Take a closer look at this picture. This is Eugene Cernan, saluting the flag of the United States, the last astronaut from the Apollo program to set foot on the moon. But there's something odd here. Do you notice it? There is not a single star to be seen in the background. In fact, every photo taken during the Apollo missions shows a sky utterly empty of stars. Despite the universe being filled with trillions of stars, Apollo astronauts reported that they couldn't see a single star from the moon. This absence of stars has sparked conspiracy theories for years. Some even claim it's proof that the moon landing was a hoax. But the real explanation is far more fascinating and dives deeper than any conspiracy theory could. Why is space so black? This question was first purposed by Johannes Kepler back in 1610. Our Milky Way galaxy alone is estimated to contain anywhere from 100 to 400 billion stars, and the observable universe is estimated to contain 100 to 200 billion galaxies. Couldn't every patch of the sky be uniformly bright and filled with light? Surprisingly, it's not, and this puzzled astronomers for centuries. Careful analysis suggests that the sky should be as bright as the surface of the sun. Yet, when we look up at night, we see mostly darkness. This paradox, known as Olber's paradox, took nearly 300 years to resolve. The paradox of Olber's had emerged from the steady-state theory. Imagine a universe where everything has always been the same and always will be. The stars, the galaxies, all of it, unchanged forever. This is the core idea behind the steady-state theory, which was once the leading explanation of the universe. It proposed that the universe was infinite, without a beginning or end, uniform in every direction, and importantly, it did not expand. With this theory in mind, astronomers faced a question: why is the night sky dark? If the universe has always existed and is filled with stars, then shouldn't all of the night sky be as bright as the sun? According to the steady-state theory, even the light from the most distant stars should have reached us by now, lighting up the sky with their collective glow. One early explanation suggested maybe the stars were just too far away to affect our night sky, but this idea didn't hold up under the steady-state model. The age of the universe is infinite, giving plenty of time for the light from any star, no matter how distant, to travel to Earth. This light should fill the sky, leaving no dark patches behind. Johannes Kepler had a different idea to solve the paradox, and it went against the popular theory of his time. He suggested that the universe wasn't infinite after all. Instead, he proposed that the stars only spread out to a certain limit, and beyond that, there was just empty space. This idea was intriguing, but it raised some big questions. How far does this space with stars go? And what's beyond that edge? Kepler's idea of a universe with limits also came with its own set of problems. If the universe had a boundary, the combined gravity of all the stars and planets could potentially pull everything back together, leading to a collapse of the universe. Because of these challenges, most astronomers kept believing that the universe was infinite. This meant that the paradox and the idea of a steady universe were left unresolved and forgotten for nearly 200 years. Then, a famous German astronomer named Heinrich Wilhelm Olbers brought attention back to this old question, asking again, why is the night sky dark? Since then, Olber's name has become closely linked with the paradox. In his time, people still believed that the universe was unchanging, endlessly old, and infinitely large. Olbers proposed a straightforward idea. If the universe is infinite, then it makes sense that there would be endless amounts of dust and rocks in it. These particles could block the light from distant stars, causing them to look dimmer from our perspective. This dust and rocks in space absorb and block starlight as they move through the cosmos. Today, many people still believe this theory, comparing it to how clouds can block sunlight and obscure our view of the sky. Just like clouds, cosmic dust and rocks can hide the light from stars. However, Olber's explanation wasn't a complete solution. Over time, the dust and rocks that block the light would heat up and start to glow themselves. This means the universe would still be filled with light, just like before. The dust and rocks just temporarily hide the light from the stars before releasing it again. So, the overall amount of light reaching us would still be the same. So, what really solves this paradox? It took another 100 years to find the real answer to the paradox. In 1929, Edwin Hubble used his powerful telescope, hoping to find signs of the universe shrinking. This would support the idea of a finite universe, just like Kepler had suggested. But instead, Hubble was surprised to find that the universe was not collapsing. Rather, he saw that galaxies were moving away from us, and the farther a galaxy was, the faster it seemed to be moving away. This showed that the universe was not staying the same or collapsing, but was actually expanding. This discovery led to a new question. What does an expanding universe mean for its beginning? Scientists now think that the universe started as something incredibly tiny and dense. It then expanded very quickly, a process called cosmic inflation. As it expanded, it cooled down, and eventually, stars and galaxies began to form. This understanding helped develop what we now call the Big Bang theory. Scientists believe this all started about 13.8 billion years ago, and it's currently our best explanation of how our universe was born. Today, most scientists agree that the universe is about 13.8 billion years old. When we look at light that's 13.8 billion years old, we don't see stars, not because the light hasn't reached us, but because we are looking back to a time before stars even existed, a time when the universe had no stars at all. The farther we look into space, the further back in time we are seeing, until we reach what seems like the edge of the universe. This isn't a real edge, but rather the oldest light we can see, known as the cosmic microwave background. It's the leftover glow from the Big Bang and marks the farthest point we can see from Earth. When we use telescopes to look beyond the earliest stars, we see a special type of light. This isn't light from stars, but light that's left over from the Big Bang. It forms a kind of background glow beyond where the stars are. However, the Big Bang theory brings up a new issue. It suggests that the universe used to be much brighter, especially during a time called the recombination era. Back then, the whole sky would have been as bright as the sun because the universe was very hot. This means that the background glow from the Big Bang, known as cosmic background radiation, should be very bright. According to Olber's paradox, this bright background should make it hard for us to see any faint stars in the night sky. Since the Big Bang happened 13.8 billion years ago, the universe has been following three main rules as it grows and changes. First, at the very beginning, the universe was extremely tiny, very dense, and super hot. Second, just a tiny fraction of a second after it started, the universe began to grow bigger and cooler. Third, and this is really important, the universe will keep expanding and cooling down. Astronomers believe this will go on until the universe becomes so cold that all heat disappears. They call this the heat death of the universe, sometimes also known as the Big Freeze. In this future scenario, the universe has expanded so much that it has cooled down completely and all heat energy has gone away. All these rules show us that our universe has been getting bigger for the last 13.8 billion years. When the universe started, it was filled with very bright and hot light. As the universe has expanded, this light has been stretched out. This stretching has turned the light into longer wavelengths, which means it's cooler and not as bright as before. This is what we call the redshift effect. It's the reason why the cosmic background radiation we see today isn't extremely bright and doesn't light up the sky like it used to. With the discovery of redshift and cosmic background radiation, we can now say with certainty that the solution to Olber's paradox is the Big Bang and the expansion of the universe. The The universe was born from a singularity and expanded rapidly during the Big Bang, cooling down over billions of years. The finite age of the universe means that there is a limit to how far we can see, and the redshift effect ensures that the light we observe from distant objects is faint, leading to the dark night sky we see today. Thanks to the discovery of redshift and cosmic background radiation, we now understand that the Big Bang and the expansion of the universe solve Olber's paradox. The universe started from a single point and quickly grew during the Big Bang. Over billions of years, it has cooled down. Because the universe isn't infinitely old, there's a limit to how far we can see into space. The redshift effect also makes the light from faraway objects appear dimmer. These factors combine to give us the dark night sky we see today. The fact that the night sky is dark shows us that the universe is always changing and growing. Seeing a dark sky instead of a bright one tells us that the universe started with the Big Bang and has been expanding ever since. The night sky is like a quiet reminder of how the universe began as a very hot and dense place and has grown into the huge, cool space we live in now. This insight helps solve Olber's paradox and also makes us appreciate just how amazing and complex the universe really is. Given the billions of years of evolution for the universe, life elsewhere in the universe has undoubtedly emerged. Albert Einstein once said that with so many Earth-like planets out there, there must be life somewhere else in the universe. We're not alone. A recent survey by Pew Research Center found that 2/3 of Americans believe aliens exist. Over half think that UFOs seen by military people are probably signs of intelligent life from other planets. Thanks to big improvements in space science, scientists are now more hopeful than ever that we might find alien life in the next few years. One of the well-known astronomers at Search for Extraterrestrial Intelligence has confidently expressed that within the next 20 years, we will definitely find clear proof of intelligent life beyond Earth. As we continue to explore the vast universe and discover thousands of new planets, one old question still haunts us: is anyone else out there? The huge size of the universe, filled with countless galaxies, stars, and planets, makes it clear that there could be life somewhere else, even if life starting on Earth was a rare event. The universe is so big that it's like a vast blank canvas where many different forms of life could appear. This might include all kinds of intelligent beings, from the simplest to the most advanced. Imagine floating alone in the endless quiet of space. It might feel silent and empty, and you might think you're completely alone. But remember, inside our bodies, there are many small ecosystems we often overlook. Countless tiny organisms and microbes live on our skin and in our guts, even though we don't notice them. These tiny creatures might not be smart like us, but their presence shows that we're never truly alone. This suggests that many forms of life may exist in the universe. Given the age of the universe, it's possible that various life forms could exist elsewhere. On planets far away, creatures might have developed amazing mental abilities because of their unique environments and evolution. Some of these alien civilizations might be less developed, similar to how humans were long ago. They might know simple ways to communicate, use basic tools, and have a limited understanding of the universe. But other civilizations could be far more advanced than us. These aliens might have incredible intelligence, mastering advanced technology and space travel. Their knowledge and culture might be so far beyond ours that they seem almost like gods to us. The diversity of intelligence in the universe goes beyond our imagination. In truth, what we think of as progress might look very small compared to the whole galaxy. To better understand how vast the universe is, and our place in it, scientists and thinkers use different scales and methods. One method, called the Kardashev scale, was created by Russian scientist Nikolai Kardashev in 1964. It helps classify civilizations by how much energy they use and how advanced their technology is. This scale is a useful tool for thinking about where we might be heading as a species. The Kardashev scale is a system with 4 levels that ranks civilizations by how well they can use energy. It's based on the idea that the more advanced a civilization's technology is, the more energy it can use. A Type 1 civilization, also called a planetary civilization, can use all the energy available on its home planet. This means they use things like solar, wind, and geothermal energy to run their industries and meet their energy needs. They can control the resources of their entire planet. A Type 1 civilization is not limited to a single planet, but has established a presence on multiple planets and moons. Within their solar system, they have formed a unified government that spans across these planets and enables interplanetary trade, research, and collaboration. Their technological advancements have enabled them to augment themselves and their capabilities. A Type 2 civilization, also known as a stellar civilization, can use the energy from their own star. They might build huge structures like Dyson spheres or Dyson swarms that surround their star and capture its energy. This type of civilization can use the huge resources of their solar system to power their advanced technologies and explore other stars. Each tenth of a number in the Kardashev scale equates to an order of magnitude of power utilization potential. A Type 2 has 10 orders of magnitude more power at its disposal than a Type 1, or alternatively worded 10 billion times as much power. The same difference in power between a nuke and a toddler's punch. A Type 3 civilization, also known as a galactic civilization, can use the energy from their entire galaxy. They might be able to move planets, use stars to power black holes, and even change the structure of space-time. And at the last, a Type 4 civilization would be capable of creating a universe itself, meaning multiverse, and can control these universes. Imagine a scale that measures how advanced a civilization is based on how much energy they can use. We're not even at the level 1, but we're definitely using more energy than ever before. Some scientists say that if we keep increasing our energy use by 3% every year, it could take between 100 and 200 years to reach Type 1. At that point, we'd be able to harness all the sun, wind, and water power we could ever want. Imagine controlling the weather, even building cities that float. That's the kind of power we might have in the future. Just like civilizations use different amounts of energy, they probably also use different ways to talk to each other. Imagine a civilization that can use all the power on their planet. They might still rely on radio waves or light signals to send messages, like we do today. But as civilizations get even more advanced, they might invent totally new ways to communicate, faster and more complex than anything we can imagine. Imagine civilizations so advanced they can harness all the power from their star. Type 2, civilization might be sending messages through ripples in space-time or using some mind-blowing tech called quantum entanglement. And Type 3 civilization might be using shortcuts like wormholes or even talking through some kind of space tunnel to travel to other galaxies. As we started our journey toward becoming a Type 1 civilization, we first tried to reach out to outer space. We sent messages in different forms to say hello and show our curiosity about the universe. One of the first big efforts to talk to aliens was the Voyager Golden Records. The Voyager Golden Record, put together by a team led by Carl Sagan, included sounds, pictures, and music from Earth to show the variety of life and cultures we have. The Voyager space probe is now 14 billion miles away from Earth, making it the farthest object we have sent into space. It carries messages that show our curiosity and wish to make contact with others in space. However, sending these messages comes with big challenges. Space is incredibly vast and mostly empty, which makes it very hard for any alien civilization to find our small plaques and records by chance. The huge distances make it unlikely that these messages will ever meet anyone out there. The vast distances between stars and planets mean that messages we send into space could take hundreds or even thousands of years to reach their destination. For example, if anyone ever found the Voyager Golden Records and replied, their message would take ages to get back to us. These long times make it very hard to have quick conversations or share information quickly with beings from other stars, limiting our chances for fast communication and learning from each other. Scientists around the world use radio telescopes to search the skies. They look for the special, narrowband signals that are different from the usual noise in space. These telescopes help scientists listen to the universe's faint signals. It's similar to how you tune into a specific station on your FM radio. Scientists often look for signals in a part of the radio spectrum called the water hole, which includes frequencies close to those naturally emitted by hydrogen and hydroxyl. These elements are common in the universe, making their frequencies good choices for trying to communicate across space. A big challenge we face is the language barrier. Language is fundamental for humans to share ideas, feelings, and knowledge. But when it comes to communicating with extraterrestrial beings, understanding their language becomes tricky. How can we interpret the signals or codes from an alien civilization? What methods might they use to communicate? These are the key questions that scientists and researchers deal with in their search for extraterrestrial intelligence. Mathematics is often considered a universal language, one that goes beyond cultural and linguistic differences. By using mathematical concepts, we might find a way to communicate with alien civilizations. Basic ideas like addition, subtraction, multiplication, and division apply everywhere and could provide a foundation for exchanging messages with beings from other worlds. No matter where you are in the universe, some basic truths remain the same, such as 2 plus 2 equals 4, and the ratio of a circle's circumference to its diameter is about 3.14. Even if different civilizations use different symbols for numbers, the basic maths concepts don't change. One way we might communicate with aliens using maths is through bits. In digital communication, a bit is the smallest piece of information and can be a 0 or a 1. By putting together a series of bits, we can create and send messages. For example, we could assign a unique series of bits to each letter of the alphabet, creating a binary code for written communication. In this code, 1 bit could represent the letter A, 2 bits could represent B, and so on. This binary code could be a starting point for communication, allowing us to send longer messages that might be understood by an intelligent alien civilization. Using this method shows aliens that we understand maths. However, crafting a message that aliens can understand would be one of the biggest intellectual challenges humans have ever faced. Actually, having a conversation with aliens might be extremely difficult, if not nearly impossible. Even if there are potential risks in reaching out, it's too late to hide our existence. Any civilization capable of traveling between stars could already detect the radio and TV signals that have been escaping into space from Earth. Active SETI projects doesn't really increase our risk. Given what we know now, it's possible that we might make contact with another civilization soon. It's also possible that a civilization has already heard our messages but chosen not to respond, perhaps because they prefer it that way. All these efforts are part of what's called active SETI or METI, which stands for Messaging Extraterrestrial Intelligence. This involves deliberately sending messages or signals from Earth into space. By actively trying to communicate, scientists hope to catch the attention of intelligent beings who might be listening and able to receive these signals. Moving from just watching to actively sending messages shows a growing belief that humanity should take an active role in trying to make contact with other civilizations. Nevertheless, we have yet to find any evidence of aliens. This problem is known as the Fermi Paradox, named after the renowned physicist Enrico Fermi. During a lunch conversation with his colleagues, Fermi famously asked a simple yet profound question: "So where is everybody?" This question highlights the puzzling absence of any confirmed contact or evidence of alien civilizations, especially given the vast number of places they could potentially exist. It's possible that more advanced civilizations simply choose not to communicate with us. Given our current level of development, they might not see a reason to. The technology needed for interstellar travel would likely be available only to civilizations that have reached at least a Type 2 level, and from their perspective, we might not seem significant enough to engage with. It's like asking why a person would try to have a meaningful conversation with ants. How would an ant even recognize that someone is trying to communicate with it? Compared to these advanced civilizations, we might seem like highly developed ants that have taken over a planet. This idea is known as the zoo hypothesis. It suggests that extraterrestrials might have decided not to contact us or reveal themselves for several reasons. They might want to let us develop and evolve on our own without interference. They could also be trying to avoid potential conflicts or cultural clashes, or they might simply not be interested in communicating with a civilization that's less advanced than theirs. Another explanation for the Fermi Paradox might be that we have already received signals from other civilizations, but we didn't recognize them. Maybe we haven't noticed these signals, or we don't have the ability to understand or decode them yet. There have been some unusual signals detected from space that are still being studied, raising big questions for scientists. One of the most well-known of these signals was detected in 1977 by the Big Ear radio telescope at Ohio State University. During a search for signals from other civilizations, they detected a strong, unusual signal spread across a frequency range. On the night of July 15, 1977, Jerry Amon, a professor at Ohio State University and a volunteer for the SETI project, was monitoring the signals. He noticed a strange signal recorded by the computer on a printout. This signal later turned out to be the strongest unusual signal ever picked up by a radio telescope at that time. The signal lasted for 72 seconds and was 30 times stronger than typical background signals. It originated from the direction of the constellation Sagittarius. The computer translated the received signals into a series of alphanumeric characters, creating the now famous sequence 6EQJ5. This suggested that the source of the sound was broadcasting regularly, similar to how a lighthouse beam sweeps across the sea, lighting up different areas as it rotates. It seemed as though we caught a glimpse of the signal when we were facing it and then lost it as we turned away. However, the signal was not consistently detected. Because of the design of the Big Ear telescope, there was a delay of a few minutes before its second receiver could check the same area of space from which the WOW signal originated. By the time it was able to look, the signal had disappeared. In fact, the signal was so astonishing that when the technician reviewed the printout the next morning, he wrote WOW in the margin. This reaction led to the name WOW signal, which has continued to intrigue the international scientific community to this day. It's possible that someday we might detect another signal like the WOW signal and discover it's not of alien origin. However, there's an important technical approach to consider. If I were leading the research, I would aim my telescope at the part of the sky where the WOW signal was detected and kept there for an extended period. This way, if any other signals were to come from that same area, I wouldn't miss them. However, it's important to consider how the Big Ear telescope was designed. In order to find evidence of alien life, researchers at Ohio State University prepared a special telescope named Big Ear as part of their quest to find evidence of alien life. This is significant because it raises the possibility of confirmation bias influencing their findings. Big Ear was huge, about the size of 3 football fields. It functioned similarly to modern telescopes. It captured signals with a large mirror at one end, which then bounced them off smaller mirrors at the other end. The signals were directed into 2 receivers in the middle where the data were processed. You may notice that these capture dishes are just wireframes though, not true mirrors. This is because Big Ear was a radio telescope. It wasn't trying to see with visible light. Big Ear was more limited in its motion compared to a telescope that could rotate freely. It could only tilt its primary reflector up and down, so it could only focus on a narrow strip of space at a time. This design was cheaper and easier to build. However, the designers had a clever idea to overcome this limitation. They built Big Ear in such a way that the rotation of the Earth would move it left and right, with the Earth's rotation handling one direction and the tilting reflector adjusting along the other axis. Big Ear could eventually point to any spot in the sky if you waited long enough. It was a smart solution to its design constraints. But consider the way Big Ear was constructed. It moves with the rotation of the Earth, so it can't continuously monitor the same spot in the sky for more than a few moments. This limitation means we don't know if more signals came from that area of space. It's possible that numerous signals, even something as complex as an entire orchestra performance, could have been broadcast from that region in the hours following the WOW signal. But since Big Ear wasn't focused on that spot for more than a brief moment, it might have only caught a single note from the potential symphony of signals. This approach highlights a deliberate choice by organizations like SETI, which are searching for intelligent life in the universe. Because resources are limited and space is vast, they can't afford to point a telescope at a single spot for decades, hoping aliens will respond from that location. Instead, they prefer to sweep across wide areas of space to cover as much ground as possible, hoping to get a lucky hit. It's like fishing. Rather than leaving their line in the water at one spot, they keep casting and casting, seeing if anything bites right away, and moving on if nothing does. This approach is more reasonable than an analogy makes it sound, as aliens are not fish to be attracted to a lure or scared off by a splash of a telescope looking at them. And although the first process is more methodical, there's every chance that if you just sweep your telescope across the sky, you will encounter some evidence or signal. The problem comes with the follow-up. There have actually been numerous signals, like the WOW signal that radio telescopes have picked up over the years, strange and unusual bursts that we have no current explanation for. But because we aren't focusing on them and thoroughly following up over years of continued dedicated study, we are missing a lot of information. And as a result, we end up with weaker conclusions. Which brings us to our conclusion. Perhaps we are seeing no intelligent life simply because of our method. Of course, these are just a few of many possible theories. For this video, I've focused on some of the technical challenges in finding signs of alien life. However, there are also many theory-based explanations that are more speculative. These theories are fascinating and offer intriguing insights into our own civilization. If you enjoyed this topic, I'll explore these theories in another video. Do you think there are aliens up in the night sky? If so, why do you think they've not spoken to us? Eamon and his team thoroughly investigated the signal and confirmed that it wasn't caused by any interference from Earth. Despite their efforts, when the radio telescope operators tried to detect the signal again over the next month, they couldn't find it. Since then, astronomers have repeatedly scanned the same part of the sky, hoping to detect the WOW signal once more, but it has never reappeared. Today, the origin of that signal is still a mystery. Our galaxy alone has hundreds of billions of stars, and there are billions of galaxies in the universe. Even if life exists on just a tiny fraction of those planets, it means life is widespread throughout the universe. Driven by curiosity and a thirst for exploration, humans have begun the search for intelligent life, hoping to find it or be found. The first contact might not happen in our lifetimes, but whenever it does, it will be a monumental event for humanity. What will happen after that? What will it mean if we receive and confirm a signal from extraterrestrials? How would this impact our lives, our priorities, our view of the world, and our own identity? Will we be ready for such a discovery? The real challenge for SETI research is to find a signal as striking as the WOW signal that can be detected consistently, not just once. This repeatability would be crucial for confirming the existence of extraterrestrial intelligence. For us to find or contact an alien civilization, one of two things needs to happen. Either we send a message and they reply, or they send a message to us first. There are different ways to do this. like sending spaceships or unmanned probes. But sending spaceships is very difficult. At the speeds our spaceships can go, it would take millions of years to reach another star. For example, the Voyager 2 probe took about 49 years just to leave our solar system. The closest star is 4 light-years away, which would take over 81,000 years to reach with our current technology, about 2,700 human generations. And that's assuming the nearest aliens are at that closest star. Even if our technology improves, it takes a huge amount of energy to accelerate something to the speed of light. Actually, it would take more energy than exists in the universe. Objects just can't travel that fast. So, unless we or aliens find a new way, the easiest way to communicate is by sending radio signals. It's possible that this speed limit will be broken someday. Scientists have some ideas, like moving space around you with warp bubbles instead of moving yourself. The speed of light limit only applies to movement in a local area, so if the local area is moving, you're okay. Let's just go with the fact that it's much easier to call than to visit in person. It's significantly easier and cheaper to send out light or radio waves as simple as turning on a sufficiently large light bulb. So, let's assume that this is how our first contact with aliens will occur. Even here, however, we hit a roadblock. Radio signals and light are more than capable of traveling at relativistic speeds. It's called the speed of light for a reason, after all. However, that's its limit, light speed, just under 300 million meters per second. No signal can go faster than that. And this, in turn, limits how far we are able to see through space. Any signal from us would need to travel out across space before reaching alien life. And then, even if they decide to respond immediately, their response would need to travel all the way back. If they decided to respond. Let's imagine that happens though. We only invented the radio in the mid-1890s, so we have not really been able to do this for very long. As such, we would only be able to exchange a message with aliens who lived at most 60 light-years away from us. 60 years for a signal sent out in 1900 to reach the alien civilization, and 60 years for it to come back. Our galaxy is roughly 100,000 light-years across. In 1972, an extraordinary spacecraft named Pioneer 10 embarked on an exciting mission to explore the asteroid belt and the massive gas giants in the outer reaches of our solar system. Traveling at a speed of 32,000 miles per hour, Pioneer 10 set off from Earth on a journey that would pave the way for future missions like the Voyager probes. Pioneer 10's mission was a remarkable success, but it wasn't without its challenges. Little did we know, the probe carried a hidden problem. A riddle that would puzzle scientists for decades. Nicknamed as the luckiest spacecraft ever launched, Pioneer 10 faced numerous malfunctions. In the early 1980s, while the probe was still communicating with Earth, scientists noticed something strange. Pioneer 10 was slowing down and veering off course, as if an unknown force was pulling it back towards the sun. For about 15 years, researchers conducted extensive studies and analyzed data, but they couldn't solve the mystery. The unexplained slowdown eventually stopped, leaving behind one of the greatest enigmas in spaceflight history. This phenomenon, known as the Pioneer Anomaly, remains unsolved. Even today, the flyby anomaly continues to puzzle scientists. This glitch challenges our understanding of spaceflight and keeps us searching for answers. The Pioneer Anomaly is a reminder that, despite our advances in space exploration, there are still mysteries in the universe that test our knowledge and ignite our curiosity. Launched in 1972, Pioneer 10 was NASA's groundbreaking mission to explore the outer planets. The probe was named after the brave pioneers who settled the western United States, as it aimed to boldly go where no spacecraft had gone before. Pioneer 10 achieved remarkable milestones, including several firsts in space exploration. It was the first spacecraft to travel beyond Mars, cross the asteroid belt, and reach the gas giant Jupiter. Pioneer 10 also made history as the first spacecraft to use an all-nuclear power supply and follow a path that would take it beyond our solar system. Although it was originally intended for a 21-month mission, Pioneer 10 far exceeded expectations, operating for over 30 years. In January 2003, after a long and distant journey, the probe sent its final signal back to Earth. Today, Pioneer 10 continues its voyage, drifting like a ghost ship through the cold expanse of space, more than 11 billion miles away, moving in the opposite direction of the Sun's motion through the galaxy. Twin to Pioneer 10, Pioneer 11 launched a year later in 1973, embarking on its own journey into the great unknown. Like its predecessor, it became the second probe to pass Mars, navigate the asteroid belt, and reach the giant planet Jupiter. Pioneer 11 then made history as the first spacecraft to fly by Saturn. Unlike its twin, however, Pioneer 11 left Saturn on a different path, heading out of the solar system at a 90-degree angle to Pioneer 10, towards the center of the galaxy, in the direction of the constellation Sagittarius. In 1995, NASA received the last signal from Pioneer 11, marking the end of its communication. It silently vanished into the depths of space, leaving behind a legacy of exploration. But both Pioneer 10 and 11 left behind a puzzle that would baffle physicists for decades. Shortly after Pioneer 10 and 11 ventured beyond the orbits of Jupiter and Saturn, their navigators noticed something strange. Both spacecraft were slowing down more than expected, as if an unknown force was gently pulling them back towards the Sun. While some deceleration due to the Sun's gravity was anticipated, the data showed an excessive slowdown that couldn't be easily explained. The deceleration was incredibly small, just 1/10 billionth of Earth's gravitational acceleration. In 1998, John Anderson of JPL and his colleagues calculated that the spacecraft were decelerating at a rate of about 300 inches per day. While this difference seemed tiny, it had significant implications. The Pioneers ended up thousands of kilometers closer to Earth each year than expected, eventually falling short of their predicted locations by distances similar to the gap between Earth and the Moon. Year after year, the spacecraft deviated by a few thousand kilometers from their expected positions. Initially, this didn't raise many concerns, but as time passed, it became clear that this tiny deceleration persisted as the spacecraft traveled deeper into space. The Pioneer anomaly remains one of the greatest mysteries in space exploration, challenging our understanding and sparking curiosity about the forces at play in the cosmos. This mystery adds to the many questions we have about the universe, pushing us to seek answers and explore further. As we dive deeper into the mysteries of the universe, we find that everything we see, like stars and galaxies, is made of matter. Matter makes up about 5% of the universe and includes all the atoms and particles of the universe. Next, we have dark matter, which accounts for about 27% of the universe. We can't see dark matter, but we know it's there because of its gravitational effects on visible matter. It's like an invisible framework that helps shape and form galaxies. The biggest and most puzzling component is dark energy, making up about 68% of the universe. This mysterious force is causing the universe to expand faster. Together, matter, and dark energy create the fabric of the universe, from the tiniest particles to the largest galactic structures. While we don't fully understand what dark matter and dark energy are, we are fairly confident they exist. Here's what we know. Dark matter is crucial for galaxies to form. When scientists studied the structure of the universe, they realized there wasn't enough regular matter to explain how galaxies and complex systems are created. The gravitational pull of visible matter alone isn't strong enough to form galaxies. Without dark matter, stars would probably be scattered randomly instead of forming the beautiful galaxies we see. This suggests that dark matter acts like a glue, holding galaxies together. Dark matter is a mysterious component that neither emits nor reflects light. making it invisible. However, we can indirectly observe dark matter through a phenomenon known as gravitational lensing. Areas with high concentrations of dark matter bend light that passes close by, acting as a clue and revealing its presence through gravitational interactions. We know that dark matter isn't just ordinary matter without stars. Ordinary matter emits detectable particles, making it visible to our instruments. If dark matter were simply ordinary matter, we would have already observed it. This tells us that dark matter is something different, adding to the mystery and driving further research. Dark matter also isn't antimatter. Antimatter emits unique gamma rays when it reacts with regular matter. If dark matter were antimatter, we would detect these gamma rays, but we haven't. Additionally, dark matter isn't made up of black holes. Black holes are dense objects that dramatically affect their surroundings, while dark matter appears to be spread out across the universe. The gravitational effects of black holes differ from what we observe with dark matter. Scientists are exploring various hypotheses and conducting experiments to uncover the true nature of dark matter. Despite the mystery, these efforts continue to bring us closer to understanding this elusive substance. Even the ultra-precise 15-month survey of the cosmos by the European Space Agency's Planck spacecraft was only able to detect less than 5% of the total of the observable universe. For years, scientists have been trying to solve the mystery of dark matter. They have been able to infer the existence of dark matter only from the gravitational effect it seems to have on visible matter. Renowned British physicist Brian Cox explains about dark matter and considers it as some kind of particle that we are currently unknown.
We're absolutely sure now it's there from many different measurements, from the way that galaxies rotate, the way that galaxies interact with each other, and the whole evolution of the universe actually requires there to be dark matter, about 5 times as much dark matter as there is matter. So it completely outweighs the stuff out of which we are made, and all the stars we can see in the sky are made. So it doesn't glow, it's not stars, which is why it's called dark matter. What is it? It is, as a particle physicist, I would say it's probably, but that's an unscientific thing to say, but if I had to guess, it's a new kind of particle, I would guess. So a particle which we haven't discovered yet. There are theories, many theories in particle physics that suggest that there are other particles out there that are waiting to be discovered at places like the Large Hadron Collider. And so I think the evidence tends to suggest there should be some new kind of particle. And we may discover it. We have experiments in underground laboratories that are literally looking for the dark matter that we fly through as the Earth orbits around the Sun and the solar system goes around the galaxy and the galaxy passes through the universe. We're flying through this dark matter. So it does come through. It should be in this room now and in the room where you're sitting now, but it interacts very weakly with normal matter. So we have experiments looking for the very rare times when those dark matter particles might bump into some matter. So we can look for it that way. Or we can try and make these new particles at particle accelerators like the Large Hadron Collider. So that would be my guess. It's a new kind of particle.
Dark energy is even more mysterious than dark matter. We can't directly detect or measure it, but we can see its effects. In 1929, astronomer Edwin Hubble made a groundbreaking discovery. He studied how light from distant galaxies shifts towards the red end of the spectrum as it travels through space. This phenomenon, known as redshift, revealed an astonishing truth. Hubble found that more distant galaxies showed more redshift, while closer ones showed less. He concluded that this redshift was due to the universe expanding. As light wavelengths stretch, they shift towards the red end of the spectrum, indicating that space itself is growing. Recent discoveries have taken this even further. The universe's expansion is not just continuing, it's accelerating. Previously, scientists believed that gravity would slow down or even reverse this expansion, but dark energy is driving it to speed up. Scientists have discovered that the rapid expansion of the universe is due to dark energy. This mysterious force is driving the universe apart at an ever-increasing rate. As the universe expands, space itself doesn't change its properties. There's simply more of it. New space is constantly being created everywhere. Galaxies remain tightly bound clusters held together by gravity, so we don't experience this expansion in our daily lives. However, we can observe it throughout the universe. Wherever there's empty space, more is forming every second. These discoveries about dark energy continue to challenge and expand our understanding of the cosmos. So, what is dark energy? It appears to be a type of energy intrinsic to empty space, stronger than anything else we know, and constantly increasing. Empty space holds more energy than everything else in the universe combined. This mysterious force is pushing galaxies apart and accelerating the expansion of the universe. Dark energy remains one of the greatest mysteries in cosmology. While we can't detect or measure it directly, its influence on the universe is undeniable. The discovery that the expansion of the universe is speeding up suggests that dark energy is at work. Understanding dark energy is one of the biggest challenges in cosmology today. As we continue to explore and study the cosmos, we hope to unravel the secrets of this enigmatic force, bringing us closer to understanding the true nature of our ever-expanding universe. One of the central theories in modern cosmology, the Big Bang theory, suggests an idea of how our observable universe was born. It explains the origin and evolution of the universe. Imagine the entire universe, every star, planet, and galaxy packed into an incredibly hot and dense point. That's how scientists believe it all began, about 13.8 billion years ago. Since then, it has been expanding and cooling down. This tiny point exploded in an event we call the Big Bang, and from that moment, the universe started expanding and cooling. But how do we know this happened? The theory of the Big Bang is supported by a lot of evidence. One important piece is the cosmic microwave background radiation, which is an afterglow left over from the early universe. This radiation gives us a picture of the universe just 380,000 years after the Big Bang. Before that universe was so hot and dense that we weren't able to take pictures of the Big Bang itself. Another important discovery is the redshift of galaxies. This means that galaxies are moving away from us, which shows that the universe is expanding, doubling, and doubling in size, not slowing down. This was first observed by Edwin Hubble in the 1920s. The farther away a galaxy is, the faster it seems to be moving away from us. This supports the idea that the universe was once much smaller, hotter, and denser. The Big Bang theory also explains the amounts of light elements like hydrogen, helium, and lithium in the universe. These elements were formed in the first few minutes after the Big Bang, when the universe cooled enough for protons and neutrons to make nuclei. But the Big Bang theory also raises some big questions. For example, it doesn't explain what happened before the Big Bang and how the universe formed from nothing. When we look around, we see that everything is made of tiny particles. These particles have been coming together for billions of years, forming humans, planets, stars, and galaxies, all following the same physical rules and existing in the same space and time. But there was a time when there was nothing in the universe. So where did all this stuff come from? Scientists think about this in different ways. They consider the possibility that everything came from something, but also that it might have come from nothing. But what does nothing mean in science? From a scientific perspective, there are 4 different ways to think about nothing. Let's explore each one. Let's imagine a universe with nothing in it. No stars, planets, or anything else we see. Everything we know is made of tiny particles. These particles build up to create everything around us. Starting from a universe full of stuff, we can understand how it changed over time to become what we see now. Stars, for example, change over their lifetimes, making heavier elements that lead to new stars, planets, and even life. But there's a big question. Why is our universe mostly made of matter, not equal amounts of matter and antimatter? This is a huge mystery in physics. According to the rules of physics, matter and antimatter should be made in the same amounts. But when we look at the universe, we hardly see any antimatter. It's almost all matter. So, how did we end up with more matter than antimatter? Scientists call this puzzle baryogenesis. It's about how the universe got more baryons than antibaryons when it was young. Scientists have lots of ideas, but we still don't have a clear answer. We don't know why there's more matter than antimatter instead of an equal amount. Another way to think about nothing is as the vast emptiness of space. Imagine a scenario where there's absolutely nothing. No particles, no energy, just empty space stretching on forever. In this emptiness, some scientists see the true meaning of nothingness. But even in this completely empty space, there are still some fundamental things that remain. The laws of physics are still at work, like the forces that govern how things move and interact. There are also quantum fields, which are like invisible forces that exist everywhere. These include fields like gravity and electromagnetism. Even though there's no matter or energy, there's still something called zero-point energy, which is a tiny amount of energy present even in empty space. Today, we understand this as dark energy, which is causing the universe to expand. So, even in a universe where there's absolutely nothing, there's still something happening. This idea challenges our understanding of what nothing really means and shows that even emptiness can be a fascinating part of the universe. Scientists also consider nothing as the ultimate lowest energy state possible for space and time. Right now, our universe contains something called zero-point energy, a tiny amount of energy present everywhere in space. We're not sure if this zero-point energy is the lowest possible energy or if there's an even lower state we haven't discovered yet. There's a chance we might be in what's called a false vacuum state, where the true vacuum, or the absolute lowest energy state, is very close to zero or even at zero. If the universe were to switch from this false vacuum to a true vacuum, it could lead to a major event called vacuum decay. This would cause significant changes, like photons, particles of light, gaining mass, the electromagnetic force acting over shorter distances, and less sunlight reaching Earth. Thinking of nothingness as the ultimate lowest energy state means removing all matter, energy, radiation, and any distortions in space and time. What's left is perfect emptiness, but the laws of physics still apply. In this state, there would still be a backdrop for events to happen, but without any actors or actions. It's like a play with no characters, storyline, or setting, just an empty stage. This ultimate low energy state would make it impossible to create any work, energy, or particles from it. However, some might still see this as something because space, time, and the laws of physics would still exist. Now, imagine reaching the universe's true foundational state, whatever that might be. In this state, all matter, energy, and any distortions in space-time would be removed. What would be left is the ultimate material emptiness. There would still be a backdrop for events to happen, but without any actors or actions. It's like a play with no characters, storyline, or setting, just an empty stage. This ultimate low energy state would make it impossible to create any work, energy, or particles from it. However, some might still see this as something because space, time, and the laws of physics would still exist. So, our third interpretation of nothing is the ultimate lowest energy state possible for the universe. Even in this state, the framework of space, time, and the laws of physics remain. It's another incredible mystery that keeps scientists exploring and searching for answers. Our fourth take on nothing is the most extreme. It suggests that true nothingness only occurs when the entire universe and its laws vanish completely. This concept pushes the boundaries of our understanding of reality to the limit. Imagine eliminating everything, including space, time, and even the laws that govern physics. This type of nothingness surpasses what we can grasp with physics because it signifies an absolute void, a complete absence of everything. From a physics perspective, this idea poses a challenge. How can something like space-time exist if there's no space or time? How can the laws of physics operate without a framework for them? This form of nothing is difficult to grasp and may lack any real-world significance. Thinking about this ultimate nothingness brings up many questions without clear answers. For instance, how could space and time initiate in a realm where they don't exist? Is it conceivable to have something beyond the universe devoid of space, or something commencing without time? Envisioning absolute nothingness, a total void, presents a conundrum from a physics standpoint. It implies a state transcending the confines of space and time, from which our universe and its laws may have emerged. However, we're uncertain whether this notion holds any meaningful significance or is merely a construct of our imagination. This concept prompts many challenging inquiries. For example, how could space and time have a beginning in a place or moment where neither exists? Can we even conceive of something existing outside the universe without space or initiating without time? Where would the principles governing particles and their interactions originate? While the idea of nothingness appears philosophically comprehensive, it may lack tangible substance. It could merely serve as a tool for us to comprehend phenomena beyond our tangible reality. When scientists discuss nothing, they often assume everyone shares the same concept of what nothing entails. However, that's not always the case. Different individuals and varying contexts can alter our perception of nothing. The phrase, something from nothing, might imply the creation of entirely new things from a state of true emptiness. Yet, there's disagreement on what nothing truly represents. Ultimately, it's crucial to discern which version of nothing someone is referring to, as each holds its own boundaries and applications. However, all these notions remain influenced by our human comprehension. It's intriguing that everything we know appears to have originated from nothing.